We're going to finish up this week by looking at section 5.4. We are going to split it into two sections, so we'll do 5.4 part 1 today. We're going to do part 2 tomorrow. Part 2 and 5.5 I normally do together, but we're going to be at a good stopping point with just 5.4 part 2, so we're not doing 5.5 this week. So let's first talk about what a log function is. So a log function is the inverse of an exponential function. Okay, so what does that really mean? Well, I want to look at what it means algebraically, and then I want to look at what it means visually. And I'm going to do that using a function that we're more familiar with. Let's do the squaring function. So that's a function that takes an input, squares it, and that's how you get the output. When you take the x and the y variable and you switch them, that is the inverse. Okay? So let's switch the x and the y. So now we would have x equals y squared. But that's not something that we could type in on like the graphing calculator because it needs to have y isolated. So let's isolate y in the inverse. How would you get y by itself there? Yeah?
Square root both sides.
Right, you would square root both sides. So you would get positive or negative square root of x equals y. This is the square root function. This is the squaring function. Those two are inverses of each other. Okay? So that's how you get an inverse. Take the x and the y and switch them. Now, let's graph them and see what they look like. Okay, I'm just going to focus on, I know there is two square roots, the positive and the negative. I'm going to focus on what's happening in quadrant 1. So that means I'm only going to draw half of the parabola, and I'm only going to end up drawing one of my square root functions. So let's put in x squared. And I'm just going to do the positive square root. Let's look just at quadrant 1. So it's the standard window up to 10 on the x max, 10 on the y max, but 0 for the minimums. Let's hit graph. That's the squaring function. That's the square root function. Let's look at that. Okay, what do you notice about those two functions, how they compare to each other visually? Yeah?
They seem sort of like, I don't know how to explain it, but mirrored.
They are mirrored, yep. They are kind of mirror images of each other, but not over the x-axis or the y-axis. Does anybody have a guess what they're being mirrored over? Yeah?
Y equals x.
Yes. Remember we said we changed the x to the y, and we changed the y to the x to get the inverse? Well, if you graph the line y equals x, that's exactly what these two functions are being mirrored over. Okay? So if you were to fold this piece of paper on the black line, the red one would land right on top of the blue one. Okay, so that's what inverse functions look like visually. They are reflections of each other over the line y equals x. All right, now there's two types of tests you sometimes talk about in Algebra 1. You talk about a vertical line test. You also talk about, not as much, but it should be mentioned, a horizontal line test. So vertical line test is kind of an informal way to say if something is a function. Right? If you were taking an exam and you had to justify why something is a function, generally saying it passes the vertical line test isn't an appropriate reason, right? That's very informal. You could say for every input value of x, there is only one output value of y. That proves something is a function, right? Now, the horizontal line test is a little bit different. It still has to do with something being a function, but it has to do with the inverse of your graph being a function. So if you draw something and it passes the horizontal line test, then that means the inverse of what you're looking at is a function. Okay, so think again about the parabola, just the half of it that I drew. If I draw a horizontal line, does a parabola pass the horizontal line test? Meaning if I put a horizontal line, would it only hit that graph one time? Jake, what do you think?
Yeah.
Yeah, no matter where you draw a horizontal line, it is only going to hit the graph one time. Because it only hits the graph one time, then that means the inverse of this picture is a function. And what is the inverse of this picture? What function was it? That's a parabola. The inverse was, yeah?
Square root.
Square root, yeah. So because a parabola passes the horizontal line test, it means the square root function passes the vertical line test, because that's its inverse. Now, we can apply the exact same reasoning with logarithms and exponentials. Okay, so let me graph those. So let's graph something like, let's see, I may already have an example right here, actually. Let me see. Yeah, I do. So I'm going to go back up in a second. What you're looking at in blue is an exponential. Right? That's the kind of graphs we studied on Monday. What you're looking at in red is a logarithm. The calculator doesn't do a great job with sketching a logarithm because you had a part on an exponential that was extremely flat, right? Approaching a slope of 0. When you reflect that over the line y equals x, this part that was approaching 0 starts to approach an infinitely steep slope. The calculator can't draw things very well that get steep. Okay? So it almost looks like the logarithm function starts at -1, okay? But it shouldn't. Okay? It should go down forever. Let's graph a log. It's the same. I think it's the same log I have right there. And if you look at the log, does everyone see how it looks like it starts at -1? Now zoom in near -1 and watch what happens. Go zoom, 2. Doesn't look like it's at -1 anymore. Now it looks like it's going down a little bit lower. It's like -1.5, right? So it's, again, it can't really do a good job because it gets too steep. All right, so then if I can draw a horizontal line and it would only hit that graph in blue one time. Okay, never hits it more than once. Looks like it hits it more than once over here, but remember that blue part over here is not flat. It's still going down, just slowly. So if the blue graph passes the horizontal line test, what does that mean about the red graph? Yeah?
It's a function.
It's a function, right? The blue graph passes the horizontal line test. The red graph is the inverse of that. It means the red graph passes the vertical line test, and it is a function. So logarithms are functions. So what that means is for every value of x you plug in, you will get a unique answer for y. Logarithms are functions. And piecing that together, that's kind of important to be able to put that thinking together, that if a function passes its horizontal line test, then the inverse of it passes the vertical. Okay. Any questions on that? All right. So the next thing we talk about is how do you write a logarithm? Okay. First of all, if you were doing it on lined paper, it would look just like that. There are no exponents in there in that expression at all. The a is a subscript. It would be below the line. The y, the equals, the log, and the x are right on the line. If you had something like this, okay, now you get an exponent. But without that too, there are no exponents there. That's important to understand. And the way we read that is y equals the log base a of x. You do have to say the base. The base is kind of like the index in a square root. There's lots of, in any root. Okay, there's lots of kinds of roots. Square root, cube root, fourth root, fifth root. There's lots of kind of logarithms. Base 2, base 3, base 4, base 6. So a is, it's kind of like the index in a root. It just changes the type of root that you're doing. The part that you're plugging into the log function, that value right there, x, that is called the argument. Basically, anything that you plug into a function is called the argument. So when you do square root of 9, I mean, technically you could call 9 the argument to the square root function. We usually call it the radicand. But it is the argument. It's what you're plugging in. Now, when we do logarithms, there are two special bases that will come up quite a bit. Does anybody know one base that's very common with logarithms? Yeah?
Base 10.
Base 10. And because it is so common, that is called the common log. Common log. So generally, if somebody asked me to find, say, the log of 17, if they didn't say anything else, I would assume that they want the common log, which is base 10. Kind of like if somebody said, find root 10. It's kind of a vague question, but if they said root 10, I would assume they mean square root 10. I wouldn't assume they mean cube root 10. It would be square root. But base 10 is what we call common log, and there is a button for doing base 10 logs on the calculator, and it's on the left-hand side, right below x squared. So if you type in log 17 or log 7, you just found the common log of 7. Because base 10 comes up quite a bit, we don't have to write the base on a log when it's a 10. Kind of like when we do a square root. We do not put a 2 as the index. That's the notation. We don't have to. Same thing with log. So if you want the common log of 7, you can just write log 7. You could write log base 10 of 7, but you'll never see me do it like on the right-hand side. I would always write it the way it is on the left. Any questions on what's called the common log or where the button is on the calculator? Yes?
How
do you do subscript on calculator?
Like to put in a log with a different base. We'll talk about that. Yeah, we'll talk about that. So there is one other special log, and we did talk about this number a little bit on Monday. They said we'd do more with it today. Anybody remember the name of that special number from Monday? Yeah. Euler's number. And what number? What was it? Roughly, like about. What's the value of it?
Around 2.75?
2.718. Yeah. 2.718. And it doesn't keep repeating. It looks like it does on the calculator, 1828, because that's all the decimals the calculator will give you. But it is irrational. Okay? You can't write it as a fraction. And when you write something with a base of e, okay, this is called the natural log. These are the only two logarithms that have special names. Common log is base 10. Natural log is base e. And because we like to come up with abbreviations for things, they generally don't do log base e. They use a notation for that. And the notation is lowercase l, lowercase n. Ln. So this means exactly the same thing as that. Okay. When you use ln, you've got to be careful because it's a shorthand notation, but you can start to forget what it means. It means log base e. So the base is hidden when you use the notation ln. But you do have to remember that it is there. Okay? You have to remember what it means. So whether you write something like on the left-hand side or the right-hand side, they are equivalent. But the left-hand side is probably not something you will see. They're going to choose always, like on the test in the homework, to write it the right-hand side way. Okay, and the button for natural log is right below the button for common log. So like if you wanted to find the natural log of 13, that's it. Okay, so when we type in log, we're getting these numbers that are decimals, but what are they? Does anybody know what those numbers mean? They represent something. You know what those numbers represent? Like that 0.845. That is something. It's the answer to some kind of equation. What's the base on that log? Even though it's not written, we talked about what it is. It's 10. Base is a 10. If you wanted to figure out what power can you raise 10 to and get 7 as the answer, it's 0.84509. So let's try it. Take 10 and raise it to the 0.845098. And you get 7. Right? So when you solve and you type log into the calculator and you hit enter, the answer that you're getting is an exponent. Logarithms are exponents. That's what they are. They are used to solve equations that have variables and exponents. So now that's how it ties in with what we did in the last section. This is an exponential equation. And if you had to solve it, you're going to be trying to figure out the variable, but it's in the exponent, so you would need a logarithm to do it. I have to explain how you'd know when you have this problem. How do you know to type that into the calculator to solve for the variable? Okay. Okay, so we're going to look at in that in a minute. Okay, but that's what I want you to understand. Logarithms are exponents. That's what they are. Okay. So if we go back, let's look at the picture again real quick. So looking at that graph in red, that's a log function. And what does it look like the domain is for the graph in red? Oh, Raj?
X is greater than 0.
Yeah, x is greater than 0. All numbers that are greater than 0. There is a vertical asymptote in the log function because there was a horizontal asymptote in the exponential. Remember, they're inverses, so they change. The asymptotes kind of change from horizontal to vertical. How about the range? What does it look like the range is for the log function? Oh, Dario?
All real numbers?
Yeah, it's all real numbers. Now, exponential functions go up extremely fast. Logarithms go up extremely slow. So when you look at this log function, go to your table. If x is 400, you're only at a y value of 2.6. So think about that. You've gone 400 units to the right, and you haven't even gone up 3. If you go all the way out to like 10,000 units on the x-axis, now you've just hit 4. So that's as flat of a function as you can get without being horizontal. Right? It goes up extremely, extremely slow. Right? Even by the time you get out to like 100,000 or even a million, when x is a million, you're going to be at 7 on the y-axis. So you just barely have gone up at all. But you do keep going up forever. Okay, it's the only function I know of that the slope approaches 0 as x approaches infinity. The slope approaches 0. Okay, so domain and range we just talked about. Okay, when you are finding domain, that can change. Okay, depending on if you reflect it, stretch it, flip it, domain can change. Range cannot. When you're dealing with range, it goes up forever, it goes down forever. Doesn't matter how you transform that. It's still going to go up and down forever. All right, so what we want to look at is converting between log form and exponential form. So this is more of a pattern that you need to recognize and how you change one type of equation into the other. Since logarithms only have a domain greater than 0, that's all we're going to consider here for the values I'm about to use. Okay, values greater than 0. If you try to take the log of a negative number, it's not that you can't do it, it's just that it comes out imaginary. Okay, so imaginary logarithms, those would be like imaginary exponents. It's generally not something that we're going to look at in this class. So let's start with what's on the left. That is an equation in log form. Equations in log form will always look something like that. There's 3 parts to it. A is what we call the base. X is the argument. And earlier I said to you that when you find a logarithm on the calculator, a logarithm is what kind of number? It's always used to solve for an exponent. Yes. Logarithm always equals the exponent. So this is an exponent. This is a base. X is an argument. And when we rewrite it in exponential form, if you can remember those three things, it'll pretty much tell you where everything goes. A was the base. So when we rewrite it without the word log, A becomes the base. Logarithm always equals the exponent. Y is an exponent. So when we rewrite it, Y is the exponent on the base. And X was the argument. And what happens if you argue with somebody all the time? You're going to end up by yourself. So I remember that. So X is the argument. You argue with someone all the time, you annoy them, you're going to end up by yourself on that side of the equation. Okay. So that's how you change between log form and exponential form. It's just a matter of taking three things and moving them to different spots. All right, so let's try that on this one. Now there is nothing you can solve because you have two variables. Right? To make this problem something you could solve, I would have to tell you like what y is. But we don't know what it is. So when you're done, I want something that looks just like that, without the word log. Right. What would go in this lower box on the left? Yep.
Y.
Remember, logarithm always equals what kind of number?
Oh, sorry. That would be 3. And, that's the exponent.
That's the exponent. Logarithms are exponents. So y would become the exponent. And the thing below the exponent, what do we call that? That's always your base. And what was the base on my log? 3. And x, that's what we're taking the log of. What do we call the thing that's being plugged into the log? Yep. Argument. And the argument is what ends up by itself. I mean, if you write it this way too, this is fine. That doesn't matter. But it has to be written one of those two ways. Now, like I said, if I had told you y was 2, now you could solve this and the x would be 9 if y was 2. But that's how you change from log form to exponential. All right, let's try this one. Okay, when we rewrite that in exponential, what is that going to look like? Yeah.
X equals 5 to the y power.
Argument ends up by itself. 5 is your base. Logarithm always equals the exponent. Again, not something we can solve, but that's how you would rewrite it in exponential form. Any question on how we rewrote that? Okay. So that's changing to exponential. Let's try the other way. Let's change to log form. Well, if we're going to write something in log form, what do you think the very first thing is we need to write down? Without this, you don't have log form. Yeah? Log, yeah. You've got to have the word log. So we've got log. Let's start with the base. Okay, what's going to be the base on my logarithm? Yeah?
1.2.
1.2. What's my logarithm going to equal? Logarithm always equals the 3. Logarithm always equals the exponent. And the thing that was by itself, that was the argument. And that's what you're plugging into the log function. So that's changing from exponential to log. Any question on that? Yes?
Can this one be written inversely as well, like with the 3 on the other side and the 1 on the other side?
Yeah, you can always use this, that's the symmetric property. You can switch the left and the right side of an equation. Yeah. Yep. All right, let's try this one. All right, so Nick, what's the first thing I would write down here? Yep, put the word log. And next step, I need my base. Marin, what's my base going to be? E, yeah. That was the base originally on the exponential. It becomes the base on the log. Right. How about Gregory? What's the logarithm going to equal there?
It's going to equal B.
B. Logarithm always equals the exponent. And the only thing left to fill in is the argument. All right. Now, that is one that we could abbreviate. How could we write this side in a shorter way? Yep.
ln 9.
Right. You could just say B equals the natural log of 9. And now if they wanted the decimal, which they don't, but if they did, you could press ln 9 and then get the answer. All right. Any question on that? All right, and let's try one more of those. Writing it in log form. Anyone think they can give me the whole thing and see if we pronounce everything properly? Yeah.
4 equals log a 24.
Log, forgot one word.
Log base 24.
No, not base 24. What's my base here? Yeah? A. Log base A of 24. So log base A of 24. Yep. And as long as you have the 4 on one side and that expression on the other, if you switch the two, that's fine. This is okay. Same thing. Any question on that? All right. Let's try this one. So this one's a little different. It just says to show that what's on the left-hand side is equivalent to what's on the right-hand side. Right? How could we show that those are equivalent? Lens?
Maybe we could change it into the exponential form and see if it actually.
Yeah, right now that's log form. The only thing I've shown you how to do is to change it to exponential. And let's see if we end up with a true statement, something we can figure out. Right now, we don't know how to figure this out. I haven't explained to you how to type base 2 log into the calculator. I've shown you how to type base 10 and base e. So the way this is written right now, we can't even work with this. So if we rewrite that in exponential form, Layla, what would my base be? Yep, base would be 2. And Declan, what would my exponent be?
Your exponent. Sorry. Your exponent would be 3.
Yep, exponent would be 3. Logarithm always equals the exponent. And what would be by itself on the other side? Yeah, the argument. If we change that to exponential form, you get 2 cubed equals 8. What's 2 cubed? Yeah, 8. So we get 8 equals 8. So yes, log base 2 of 8 equals 3. So what this is basically saying when you read that is it's saying 2 to what power gives you 8. That's what this means. 2 to what power gives you 8? And the answer is 3. Now, that one we could figure out, even if I threw a variable in there for this side, you could figure that out because even if that was a variable, 8 is a power of 2. But if that 8 was a 7, then we need to talk about how to figure that out. Okay, so we'll eventually talk about that. All right, let's try this one. This one is going to be doable only because something special is going to happen. If that 1 over 25 was like a 1 over 26, then what I'm showing you right now wouldn't work. All right. Any thoughts on how we are going to try to solve that? Yeah.
Maybe we can first change it to exponential.
Yeah, let's change it to exponential. Can you change that to exponential for me?
So it'll be 5 to the power of x equals 1/25.
Yep. 5 to the power of x equals 1/25. So what would x be? 5 to what power gives you 1/25? Yep. -2. Exactly. 5 to the 2 would give you 25, but we want it flipped. So when you make the exponent negative, that causes it to flip. Okay. Any question on that one? Again, what would you do if it wasn't a 25? Like if it was a 26 or a 27? We're gonna get there. All right, let's try this one. Log base 5 of x equals 1.5. All right. Suggestions on this one? What could we try? Well, Annalise, what do you think? What could we try here? Change it to exponential. That's all we know how to do right now, right? What would you get if you changed that to exponential?
5 to the power of 1/5
Yeah. And when you change it, you're done. Right. So when you have a variable that's the argument, and the base is a number, and what's on the other side is a number, it's very easy to solve just by changing to exponential. The variable automatically gets isolated. And now you can type, I'm not worried about typing that in. We could type it in if they want a decimal, but that's how you solve it. Okay, so that's for the variable for the argument. Now let's try putting the variable in the base. Emma, what could I try on this one?
You could make it into an exponential.
Yep, let's make that into an exponential equation. And what would your equation be?
3 equals x to the power of 2.
Yeah, so x is your base, 2 is your exponent, and 3 is the argument, which ends up by itself. Perfect. Okay, and now how would I solve for x there? Yeah,
Square root both sides.
square root of both sides. And when you take the square root of both sides, what would you normally get for the answer?
You'd get an irrational number.
Can you tell me, you don't have to give me a decimal, but just tell me what your answer would be?
I mean, you just write it as root 3, right? Or
actually, what happens when we take the square root of both sides normally? Yeah,
Plus or minus?
we get a plus or a minus. But when we're dealing with logarithms, both the base and the argument have to be positive numbers. I think I showed that earlier. If you try to take the log of a negative, you get an imaginary. And we're not going to deal with imaginaries. Same thing would happen if the base was a negative. It would come out imaginary. So normally when you take the square root of both sides, you get two answers, but with logs, you get one answer, just a positive answer. Don't put plus or minus square root of 3, just square root of 3. Okay. So that's solving with a variable in each spot. Variable in the base, variable in the argument, and then we did the variable all by itself on the other side. All right, so next thing we're going to look at is some properties of logarithms. Okay, these properties are kind of like special patterns that will occasionally come up, and if they do come up, it's going to make simplifying very easy. Just like with all other properties with logs, I'm not going to have any negative bases. I'm not going to have any negative arguments. So let's start with that one. A raised to the log base A of x. I want to see what that would simplify to. A raised to the log base A of x. First of all, is that exponential form or is that log form?
It's exponential.
That's exponential, right. Okay. Exponential looks like this. And then usually we have something on the other side. We don't have anything on the other side right now, so we could just, temporarily, we don't know what it equals, we just put it equals something. But that's exponential. Base, exponent, and something on the other side. Doesn't matter that there's a log in the exponent. That's still exponential. Something to a power equals something. Log would have to look like this. We'd have a log, a base, an argument, and then something on the other side. That's log form. That's exponential. So since that's exponential, let's rewrite it in log form and see what happens. Well, what's the very first thing we have to write down when we put something in log form? Yeah?
It'd just be log.
Log, yeah. We're going to fill this, and we're going to change it into that now. So the first thing you have to write down is the word log. What is the base? That's going to go right there. Yep, and let me, just to be clear about things, let's make that one purple, and let's make this one green. Which A is going in that spot?
Purple.
The purple one, yes. That's that one. That's your base. Logarithm always equals exponent. What? So now I'm doing this box. What's my exponent here? Yeah.
Log base A of x.
Log base A of x. And I'm going to write it the way it looks there. Log base A of x. Okay, so we've taken care of this. We used that whole thing. We just used that thing. The only box I haven't filled in yet is this one right here. And what's going to go in that box? Yes, yep.
Would it just be the question mark?
The question mark, yeah. That's the question mark. So A was my base. Logarithm always equals the exponent. That was the degree in A. That's the exponent. And what ends up by itself on the other side, that becomes your argument. So if you were going to solve this equation, what's the answer to the question mark? Yeah, x. So anytime that you have something that's written in this form, it always reduces to just x. Right, so that an example with numbers would be something like 2 raised to the log base 2 of x. That whole thing would just turn into x. Or if x was a number, it would be whatever that number is if we knew the number. Any question on that property? It's the first one. And if you forget it, it's okay. You can figure it out every time like we just did. But it's a lot faster if you recognize that pattern and just know it turns into x. Let's look at this one. Log base a of a to the x. Is that log form or is that exponential? Which one is that? Yeah, that is log form. Yeah. Right. You have log kind of on the main line. If this was your line paper, like that. That's different than the first one. That's log form. If we change it to exponential, it's going to give us a hint at what all that turns into, and it's going to turn into something extremely simple. Log base a of a to the x. We don't know what it equals, so let's just put question mark. And just to be clear, when we're writing the a's, I'll do them in different colors. What is my base? Yeah.
Would it be the purple A?
Yep, purple A is my base. Okay. What is my exponent? Yeah,
Question mark?
the question mark, that's what I don't know. Logarithm always equals the exponent. And what's going to go on the right-hand side? Yeah.
A to the x.
Yeah, the green a to the x. So now, if you had to solve that equation, what would you plug in for the question mark to make the left side equal the right side? X. Yeah. So again, this is just another pattern where if you have something written like that, the whole thing reduces to just x. Very easy to figure it out from scratch if you forget it, but it does save time if you don't. Let's look at this one. Log base a of a. Okay. First thing, is that log form or is that exponential? Yeah, that's log form. Let's just make these different colors. Purely so it's clear which a I'm talking about. We're going to change it to exponential. And when we do, it's going to give us a rule for this situation. All right, let's start with my base. What's going to go in this first box on the left? Yep. Yep, purple A. And again, right now, temporarily, I'll just put question mark there because we don't know what it equals yet. What's going to go in my exponent box? Yeah, that's the question mark. We don't know what it is yet, but we will. And then what's going to go on the other side? Yeah,
The blue end.
the blue end. That's my argument. So now, what would you fill in for the question mark to make the left side equal the right?
1.
1. Yeah. So anytime that you take log and the base and the argument match, the answer is 1. So log base 4 of 4, 1. All right, and we've got one more property of logs we're going to look at. Log base a of 1. So this is saying what happens if you take the logarithm of 1? Doesn't matter what the base is. Again, that is log form. Let's change it to exponential. Okay, don't know what it equals right now. Okay, so last one. What's my base? Yep. A is my base. What's my exponent on the A? Yep.
Question mark.
Question, we don't know. Logarithm equals the exponent. We don't know the exponent yet. What ends up on the other side? Yep,
1.
the 1. So now, what would you fill in for the question mark to make that statement true? A to what power gives you 1? Yep.
0.
0. Yeah. So anytime you take the logarithm of 1, the answer is 0. And hopefully by showing you how to change them from log to exponential form, I'm not just making things up. These are all rules from algebra. Right? Anything to the 0 power is 1. That's basically what rule 4 is. So they're all properties you've seen before. You just might not have seen them written as logarithms. You probably have seen it written as anything to the 0 power gives you 1. Well, this is the same thing, just written in a different way. All right, so we've got all our properties. Let's look at a couple examples. So the goal is to see if we can look at the example on the right, match it up with a property on the left, and then solve for x. Okay. Does example A look like it matches up with any property from the left?
Property 1.
Yeah, that is property 1. So if you didn't remember property 1, you can go through and change this to log form and solve it all from scratch. Or look at property 1, and it tells us that the answer for x is going to be what? Yeah, pi. That is the answer. The answer is whatever the argument is up here in your exponent. And we went through the reason why. Let's look at B. Log base 0.2 of 0.2 to the negative 4. Now, I said you can't have negative numbers, but I said in the base or the argument. These can't be negative. Nothing wrong with that being negative at all. That's fine. Okay. Again, if you weren't sure how to do it, you could change it to exponential form. But when you do that, what would you get? Let's just say equals x. What would you get for x in this case? Yeah, negative 4. That's property 2. All right, let's look at this one. Okay, it can be a little tough to figure out which property this is right away. But which property is that one? it is the second one. Could we make it, or could we rewrite it in a way that makes that clearer? Yeah.
Log base E of E to the power of KT.
Right, that's log base E. That's that part. And now copy the rest of it. E to the KT. Now you can see you have a base and an argument that are matching, just like property 2. And we'll just say we don't know what it equals. We'll just say it equals x. If they don't write equals x, you can always just put equals x because you don't know what it is yet. And what would x equal in this case? Yeah.
KT.
KT, whatever k times t is. Yep. How about log base 5 of 5? What would that be? Yep.
Property 3.
That's property 3. Whenever your base and argument match, your answer is always a 1. And then how about something like log base 6.2? Decimal bases are perfectly fine, just not negatives. Log base 6.2 of 1. Yeah.
That would be the fourth property.
That's the fourth property. Doesn't matter what the base is. This is basically saying 6.2 to what power would give you 1. You'd have to raise 6.2 to the 0 power. Any questions on that? I went a little bit slower through part 1 because I knew we were skipping 5.5. So the properties to combine and separate logs, that's the last thing in part 1. We're going to finish that tomorrow, and then we'll do some examples with it. And then we'll do part 2. So some of that I need to adjust. 1 through 7 is okay. 13 through 17 is fine. 21 to 27 is good. 29 to 33 is what we did not do. And that'll take probably about 10 or 15 minutes to finish that tomorrow. And then we'll do part 2. Right, so that's homework for tonight. We'll finish by 4 tomorrow, and then we'll have our first test for quarter 2 on Friday.